I'll spend three minutes for another project idea over here, really quick. Don't want to spend time for other people who are not working on this project, but just really quick. Haven't get a chance to grade everything, grade all the proposals, but I'll be able to do that maybe later today or tomorrow. You know, I got an EPA grant final report. I thought it's due today. I got so stressed. I was thinking I won't be able to grade anything of your assignments, and now I know it's due 2 months from now.
Oh, wow.
Huge pressure.
That's a pretty big difference.
Yeah. Let's wait for another 2 months and put a pressure at the end. Like you guys, right? Just start working on that at the due date.
Just like a mind student, they're fitting in grade.
Yeah, yeah. All right, so we all can enjoy the projects. Nice. So let me show you this really quick. So super awesome, very simple project to implement what? PID. Use PIC to do PID. PID controller, okay? PID controller, and a lot of times in other, all different kinds of projects, you have to use a motor or use something else to close a loop. It can be very complicated to implement it. So it's setting a barrier for students to learn how to use PID controllers. But the math is super simple. And the thing is, I invented this very simple circuit, like kind of let students practice with PID controller easily. It's a really cool project. And you can learn a lot from it. And you can talk about this during the interviews. So you have implemented PID controllers in your course project. Just talk about that, okay? Talk about the math. The math is super simple. It's just directly the equations are already put in the Arduino C. See, just that's it. You can adding more gains to it, but eventually what this does is, let me draw on the paper first, okay? 5 minutes, I promise. No more than 5 minutes, okay?
Hey Siri, set a timer.
What's that?
It actually started
We got light sensor, a light sensor, 10K resistor, and here's the LED. LED. It's emitting light to it, right? So this one changes the resistance. So for example, if you put it in a just regular room, okay, regular room, the resistance can be as low as 100 ohms. But if you have a cover on it, the resistance can go up to 1 mega ohms. And it's not linear, it goes up quickly. So as long as it's relatively dark, like any kind of 3D printing boxes, or even like this box, you put a sensor inside, even though there are like gaps, you can still light is going inside. But actually, it's considered as dark. It's at 1 mega ohms, huge. So if you have this divider, if you have this like 1 mega ohms as a voltage divider series, what you're getting here as an output. So your GPIO is reading this pin, okay? What's the voltage? 1 mega ohms. What's the voltage here? So 10K ohms in front of the 1 mega ohms. It's like a me in front of Mike Tyson, right? Or me in front of Cooper wrestling. I become nothing, okay? So this becomes nothing, and this pin is being what? Shorted to ground. Because there's a huge resistance, it's gonna drop like 99% of the voltage from VDD or VCC, okay, it doesn't matter. So it's gonna drop. So not 5 volts, whatever left here is probably only like 0.2 volts. Anyway, so it's considered as shorting circuits. So GPIO is reading what? It's digital circuits. It's 0, 1. GPIO is reading what? 0. Okay? So if you put it in the regular room like ambient light, it turns into like less than 100 ohms. This is a 10K. So the 100 ohms in front of 10K is nothing. So it's being put up to VDD. So this is considered as all the voltages are dropping across this resistor. So you are getting 1, okay, in that case. So basically you are reading 1 and 0, but in the middle there is the analog voltage range. It's still swinging around it, but it's just changing super quickly, okay? So the thing is, you can use LED. So you can use ambient light for sure, doesn't matter. But if you put a cover on it, so you are reading a what, basically? Put a cover on it. You are reading a 0, right? Okay? And then you turn on this LED a little bit, use a PWM. Okay? So so not 100%. Okay, so it's gonna be from 0% to 100%. So for example, do 50%. Do 50%. So the LED is not fully on, right? It's dimmed, and you use that one. Use that lattice as a set point. Set point. Okay, so for example, this is dark, right? Dark. This is bright. So 50%, for example, is giving you a set point here. That makes sense, right? That's a reading from GPL. It's a set point. Analog reading has to be ADC reading, okay? ADC reading. We're not talking about this anymore. ADC reading, okay? ADC. Sorry, ADC reading. It's confusing you guys. There will be a range. There will be a range. It's a ramp. It's not directly 1, 0, but there will be a ramp. So ADC readings this voltage, for example, is 2.5 volts, as in the 5 volts range. Okay, and then you are going to set up a closed loop. Closed loop. So this guy is giving a PWM, right? And this guy is going to change. Within that range, you know. So eventually, it's going to do this kind of adjustment to make this happen. You know what I mean? So whenever, at the very beginning, let's say, at the very beginning, I'm setting, this is the goal, right? But however, you turn on the power part on, right? Or part up. So what's the rating at the very beginning in the darkness? Here, right? Okay? So the pit loop, closed loop will sense it. So what's gonna happen? What's gonna happen here? Start from 0, right? It's gonna create a duty cycle. Okay? Create a duty cycle. So what's gonna happen? The brightness, so this will be brighter, right? What's gonna happen? Overshoot. It will sometimes overshoot a little bit. It can control that really well. But depending on how you control the gain. If it overshoots, it will pull it back. Okay? Right? We'll do this. So it's basically, if you probe that PWM, you are seeing a ghost wave over here, just doing this, trying to meet the goal in the middle. Because it won't be a perfect LED, it won't be a perfect sensor. So eventually it's just oscillating back and forth around that set point and trying to reach that goal. Okay, so if you are working on this project, it's a really simple circuit to build because this is basically everything. And you design a little cover, you can 3D print it, you can purchase a whatever cover on your, I'm gonna ask you to design the PCB. So eventually, you just need to implement the testing over here. So you press the button, you detect the button, and you increment that step point. And let your PID and the PIC to track your set point. You know what I mean? So for example, everything right now is already stable. It's already set to the set point. Okay. I push a push button. Let me paper. It's a really good project. Okay. So now it's ready. For example, it's ready here. Okay. It's ready here. Okay. It's doing this job. Okay. I push a push button. The set point getting incremented. What's gonna happen? You want to verify, you want to validate your PID controller, what you want to see. Okay? You do it one more time. So how do you validate the quality of the PID controller? How much the delay here, right? How fast it is able to track the set point change. And overshoot, undershoot, whatever, just look at it. It doesn't have to be perfect, but eventually it will be something like this. This is Arduino, it's showing a lot of noise because I amplified it. But you can see the step points over here. I push a push button, the PID controller is able to control it, to track it, you know. Make sense? Okay, so what's happening inside the black box is basically the LEDs getting brighter and brighter to track that set point. You can also dim it, so there will be two buttons to either increment it or decrement it. Okay, both ways. Make sense? Okay. Let's talk about exercise tools, remaining stuff. Let's do a picture here first. So tomorrow will be lab 9, and I have a lot of things ready for you guys to look at. But before we do anything, I want to let you watch the demonstration first, because if you don't have a goal in your mind, you just don't know what to do, right? So let's watch the video first, so you know what you are expected to do. That's important, right? Okay, so let's look at the final demo first. First, initialize the SPI port, and second, press Shift W to be ready to input your whistle, and press any key to start logging your data, your whistle data to the SD card. So start whistle first before you press any key, so you can make sure that it samples really fast. So make sure whenever you press a key, data is ready there, right? The data present. Yeah. So it samples really quickly. So you want to start whistling first before press the key. Otherwise, it's going to log a lot of empty data in it. So the time it takes to log the data is considered as long to the digital system, even though it's only like 1 to 2 seconds. But it's a lot of data points. It's sampling at like 25 microseconds per point. So you can imagine if you are whistling like for 1 second, how many points are being sampled. It's a lot of data. So start whistling first. So make sure the first data or the first series of data are sound waves. Okay? So I'm going to start whistling first. All right. Okay, so look at this one. 48 blocks. So 48 blocks. Just like, I think I just whistle for 2 seconds probably, okay? So one block, keep that in mind, is constant. It will be it's on the exercise as well. So that's a constant you need to know. And it's a very common number. Keep in mind, it's a very common number. It's being used as a minimum unit of writing and reading for SD cards. I'll repeat this for many times in the future, okay? Important. Which is 512. 512 bytes. It's called a page. A page, or a block. But Dr. Carlson keeps using blocks, which is fine. But you need to understand, it's also a page. So the way the writing and reading protocol for SD card for the memory components is doing block by block or page by page. So what it does is it's trying to manage that writing and reading function into a kind of, it's called API, a library function. So you don't really do every single index for every single bit or byte. So what it does is it pre-store all the bytes into an array, which is 512 arrays into array, right? Get that ready first. So just start taking, for example, you want to write a lot of data, like 128 megabytes to SD card, okay? So what you do first, or the steps are, the first you have to grab 512 bytes and put in the array first and use that write function to write that whole page to the SD card at once. So there are 2 steps. It's one of the questions over here. 2 steps. What are 2 steps? First, when you're writing to SD card, first you have to load that 512 bytes into array first, and then you use the write function directly, throw it to the SD card. That's the protocol. Very common. So most of the memory devices, including SD cards, SSD drives, are using 512 bytes as a page or block. So they're doing the writing and reading page by page or block by block. Okay? So you can see here, 48 blocks. What does that mean? I only whistle for how long? Like 2 seconds, for example, okay? 2 seconds. 48 blocks. How many bytes? Times 512, right? Yeah, it's a lot of data. Only 2 seconds, a lot of data.
24,576 bytes.
Yes. Okay? Now let's keep going. And then don't whistle for too long, okay? It's going to be a lot of data. And it's gonna, okay, so the as case in your code is called spooling. So it's actually outputting the SD card data you store in the SD card data, spool it out to the PuTTY monitor. So you'll see that process. It's like spooling things out. Asking really fast. Find a file to log all the data. Okay. So this step is to set a CSV file to save whatever has been saved in the SD card. Okay. So I'm gonna read from it and then save it into the CSV file. Settings. You just have to tell PuTTY where to save it. And here. So I'll just do it. Put it on the right.
to desktop, right? And so actually you can see the pattern.
See, that's spooling out. Case S, spooling out the data from the SD card. Okay. What's the minimum reading block size? 512. I just told you, reading and writing the same size, minimum size. It's writing block by block, page by page. Okay, so when it's being read, it's actually, even though you couldn't tell, but actually it's reading 512 by 512 bytes every time. But if you look at the pattern here, you see, because the bigger number will be longer, right, and smaller number will be smaller. But if you, whenever you see this getting spooling out, you can see that the pattern looks like a sine wave.
Here it's about the sine wave
see?
pattern, right? And
Right.
if you stop it,
It's moving like this, right?
Just let it run for maybe like 10, 15 seconds.
But definitely that's not a demo for a sine wave, right? It's not good enough. So that one will be saved in the CSV file over here. You see these are all the points, okay? And you open it up and copy it, and then plot it.
Just resave it. To go to that. It's,
So you can find out if yourself is a function generator or not, okay?
right.
Every single of us is a function
This is what
generator.
you want to show.
Okay.
In the demo.
So that's different from the one. Have we done this before? Lab A? Or lab A we are doing a little bit about whistling as well. But this is different because we are saving this to the SD card and we're taking them out for plotting. Okay? So in that case, we can save a lot more data, audio data, from the environment because the SD card can go up to like gigabytes. So for someone working on this kind of project, you can try to use this capability on the board, use the SD card module to save some analog signals and then post-process it afterwards. So you can see this is my whistle, and you can see the sample points here, right? It's about 1, 2, 3, 4, 5, 6, 7, 8. 8 points per period. Not too bad, but works. Now, Excel can resolve it, can eventually find out this is sine waves, not something else, right? So remember that number, okay? 8 points. And you, during the demonstration, you should change the sampling rate, okay? You want to see if you are getting the correct data. So you increase the sampling rate, you double it, for example. Eventually you spit out another set of sine wave. And again, you just count the number of points in one period, see if that's getting doubled. That makes sense? You double it in theory in your code, and you sample it, store it in an SD card, take it out, plot it, take a look at how many points you have in the sine wave. If it's getting doubled, roughly doubled as well, good. Lab 9, done. That's the goal. Make sense? Okay, let's see. 8 points, right? Okay, so I doubled my sampling rate, and I did another. Oh, that was already doubled.
It's about the sine wave. So like
Not this one. So I didn't double it in the demonstration since I couldn't do it. So that's why I don't want you to see that results. No, I'm kidding. I did it. Let's count. Okay. See, this is doubled. This is the original one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. About doubled. Right? It won't be perfect, but roughly. Make sense? Okay. So this is the tool. We have 3 demos in lab 9. The video shows 1 demo. The doubled sample frequency is the number 3 demo, and there's a number 1 demo which is easier. Let me show you. In lab 9. This guy. Actually, it's in lab 9. Probably have it here. So number 1, right? Number 1. So case 1. Let's take a look. First, in the code, it's provided, okay? In the template, it's provided. You fake a sine wave. You just plug in the numbers to fake a sine wave, like 26 points. Doesn't matter, like 20-something points will be good, but it's provided. It's provided in the template. It's given, right? I tell you it's a sine wave, you have to trust it. It's a sine wave. So 26 points in the sine wave is an array, okay? And so for case 1 is for testing purpose. what you do is you write, because 26 points is not too many. It's probably just one period, 2 periods, I don't know. So the thing is, you are going to write, you're going to replicate it for many periods and write it into the SD card, and then take it out and plot it. That's the number one task as a positive control. It's called positive control. Why? Because you know it's a sine wave, right? You know exactly the frequency and everything about it. So case number one is you just replicate it and put in an SD card, take it out, plot it. You see a beautiful sine wave, so you know that the system works. ADC is not involved. ADC is not involved. Everything is digitally being written into the SD card. So eventually, it's like a positive control. You know it works. Okay. So let's see how that works. I think this is something on the exercise as well. Let me just tell you which one it is. Number 2, I think, for today's. Number 2. Take a look. Oh, not number 2, sorry. Not number 2. Let me keep giving you misinformation here.
Is it number 7 on yesterday or Mondays?
Oh yeah, number 7 on yesterday's? Nope. Is it? Nope. I think I saw it earlier today. Yeah, never mind. That's all right. So let's see this one, number 1. Okay? How do you replicate it? You are given with array, right? It's a sine wave array. How to replicate it? Take a look at this first. I think let's get the structure here clear first, okay? See? It's a nested for loop. So let's ignore the top one first. Let's just look at this one. Okay? Block size.
Isn't it just saying that like for each index of the array of the sign copied over to the buffer?
Yes. Yeah, here, right? Yeah, so starting with 0, right? No. So if it reaches, then reset it, right? So if the index, because you only have 26 points in the sine wave, you don't want to just type like 1,000 points in your SQL, right? So 26 of them, like 1 period or something. And then you use the index to go through every single thing and write every single thing to the buffer, okay? And whenever the index reaches the end, you just reset it, so start from the beginning. So you're replicating the whole thing every time, right? So this is the line does that job, right? So the sign index becomes 0 whenever it reaches the max, the length, which is 26 or 25, doesn't matter. Okay? So see here. One question. Okay. So we have 26 points, for example, in the sine wave. So every time, how many points you want to write into the buffer before you throw it to the SD card? How many points? How many points you want to write into the buffer before you throw it to the SD card? 512. See if that's the case. Block size, we call this the block or page, right? Okay, so a page is 512 bytes. So this guy is 512. Okay, so whenever the index here is less than 512, what you want to do, just keep writing points to the buffer. It's just a name. I'll talk about this structure kind of data type pretty soon. But now this is just a buffer, okay, just an array. And you're writing every single point, but how many points? 512. So get that 512 points in that array first. So it's 512 bytes ready there. And after that is done, get out from that for loop. Do what? Do a write. SD card write. Okay, that's a function embedded into your MCC. So SD card write. So the 512 bytes will directly be thrown into the SD card immediately. So it's writing and reading page by page, not byte by byte. So you want to get everything into that array ready, which is here, right? Get it done first. See? And then do this, SD card write block. See, it's a write block, not write byte. So writing a block. Writing a block is an embedded function. You don't have to worry about the details. So writing from where? From the starting address. I'm going to talk about that really quickly. And writing the whole buffer. How many bytes in the whole buffer? 512 bytes. I've been repeating this for so many times today, okay? Make sure you can do it in the exam in the future. We don't have exam today. So while, see here is another embedded function from MCC. Running takes time. There are only how many lines? I'm going to show you the diagram. Let me do it here now. Several things to talk about, okay? So for SD card, there's the DIDO. That's the SPI, it's called the SPI communication protocol. I got two devices, CS, DI, DO, SCK. Okay, so that's critical for you guys as an experienced engineer, electrical engineer, to know that if you see SCK, since sometimes they label all these data DIDO in different modules. If you see SCK, you should know that it's a SPI protocol. SPI protocol can go up to 20, like 40 megahertz, I think. I forgot the number, but tens of megahertz. Let's just say 20 megahertz. It's a high-speed transmission protocol. 20 megahertz is fast for communication outside of the chip. So there's another protocol super popular. We'll do that especially for the accelerometers, I2Cs, right? So they are usually less than 1 megahertz, 100 kHz or something like that. So it's slow. But why do we still want to use I2C sometimes?
Long transmission.
Long transmission is slower, right? And others saying, oh, you remember that so clearly. Good. So what about the other advantages of using I2C? Stability, yep, could be. What else? That could be an interview question. Keep that in mind, because we can know if you have the experience of these protocols really easily. What's that?
You can mitigate EMI.
EMI, yes. Yeah, because low frequency, yes. SPI is not bad. How many pins? Keep in mind, this is serial, right? It's not parallel. Back to like 50, 60 years ago, you see the huge parallel ports on the back of the computer tower, right? So they're running like 16 bits in parallel. Sounds stupid, right? Like 16 bits in parallel. We never do this anymore outside of the chip. Too many pin resources being occupied. You want to keep your device in your pocket instead of the huge building size, right? So you want to reduce the number of pins. Imagine about like 60-bit CPU. You have to hold like 64 pins just for GPLs. That's crazy. Okay, so serial. Okay, we'll all do serial using protocols. Clock, acknowledgement, clock, whatever. Pull down, pull up, whatever. Just acknowledge that. Okay. So serial communication. Serial communication is also serial communication. What about UART? It's a very old serial communication, probably the number one, the first version of the serial. That's why many years ago, before these were invented, we just call UART serial, because we don't have other options. But now we have all the different options here. So this one has SDA, SDL. That's it. Is that amazing? Did you see the advantage of using I2C? What's the difference? Less pin resources is getting occupied. Clock, SDA, SDA. For SPI, DI to D out, DI to D out. Chip select, active low, clock. So let me put this in the exam probably in the future. If I show you a chip, if I show you a block, but didn't tell you anything else, okay? Just draw a square. Oh, SCL, sorry. What's the communication protocol being used?
SPI, I2C.
Could you tell? SCL, right? Sometimes you see SDA, sometimes you see DIDO, doesn't matter. If you see SCL, what is it?
I2C.
If you see this, what is ICK, what is it? SPI, okay? You grab a chip, look at the module, just look at it, you know exactly, you know immediately what that communication protocol is. Easy. Okay? So for SPI, sometimes you see DIDO. Sometimes you see some obsolete names. It's called MOSI and missile. Right, it's not being used anymore, but in the past they used this kind of names. So this is master out, slave in. This is master in, slave out. But obsolete names. So MOSI and missile, the SPI devices should have both. It's like a DI and DO. They were the same stuff inside, but just changing the silk screen on the PCB board. No differences internally. So for one SPI device, it could be a microcontroller, it could be a sensor, doesn't matter. It should have both. Okay? If this is the microcontroller, MCU, this is the sensor. It's called peripheral. It's very interesting because people start in the industry, we start changing the names to DIDOs, and there are just so many different versions. Just let you guys know where that comes from. Let me tell you all these versions, okay? DIDO, follower, leader, controller, peripheral. All these kind of different names. Start confusing beginners like you guys. Okay, but in this class we use DIDOs, okay? I think this is defined by Spark Fund, I think, at least. It's one of the entities using DIDOs, which makes sense. It's simple. Just digital in, digital out. Okay? You don't have to use like leader, follower, controller, peripheral. You know, it's the same thing. Okay? But however, if it's a microcontroller like this, you are working with a company. A lot of times you working with the defense companies, they are using super old chips, and you got a job with the defense companies, and you have to work with the microcontroller. You'll see missile, MOSI, what are they? Okay? It's very common. Even though PIC controllers are not very popular anymore, but why we are still learning it? Because you guys are very likely you are getting a defense job, and all these what's that called? The F-16, for example, are fighter jet, right? So all these kind of airplanes, they are still using PIC controllers, for example. Okay, you still see these labels, you should know what they are. Okay, so master in, split out. So in that case, you want to connect this one to here. So the peripherals, it could be a sensor. That could be a sensor. So the master is usually the controller, which has a brain in it, right? So it's doing all these controlling stuff and has memories and all the like some dual cores and all these kind of things. But usually the peripherals or the followers, they only have a SPI block, but nothing else. So eventually it's doing missile to MOSI and MOSI to missile, like that. Okay, in out. So for DIDOs, you do DIDO like this. Okay. Now let's come back here. Number one, it takes time. How many pins? How many digital pins for SPI? How many digital pins? Digital data pins. 2. DIDO, right? Okay, 2. So it takes time. It's a serial. You have so many different bytes. It's pumping every single bit, one by one. So it takes time. So in that case, you are writing 512 bytes. You can see here, it's actually you have to do a while function. There's a function is returning the status. So the SD card poll write complete or not, right? It's waiting. So the while loop to waiting there until it's done. It's gonna skip, jump out from that while loop and do the following ones. So we getting another little delay here. Try to, give it more time to get things done, and eventually do what? This is on the exercise, I think, for this part. I'm asking you which part actually increment the block. How that works. Let me do a picture for you guys. So SD card, how that works. If you think about the structure of it, here's SD card entire memory space, okay? So it's getting I'm horrible at drawing. But anyways, page by page, it's page. Every single one is a page, right? Every page has how many? 512 bytes, right? There are many pages, many different pages. So you got a starting address. I think the address number of bits for the address is 32 bits. However, there's another thing lets you calculate. So, if, for example, the SD card has 128 megabytes. Okay, megabytes. How many pages do you have in there? How many pages?
250,000.
You already calculated? Cool. So how do you calculate it? 128 times 1024 times 1024 is how many bytes, right? Divided by 512. Okay?
So you're saying that it's the 32-bit wide?
Oh, because it's a byte.
Hmm?
You're saying it's a 32-bit address space?
Yes,
For
yes,
this card?
yes.
So it's not 25.
Why do we need 32 bits? It's definitely an overkill, but how many bits do we need? We need to resolve this many bytes, that many different entries. 1 entry, 2 entries, 3 entries, so many entries, right?
Why'd you do 1024 times 1024?
Oh, because that's 2 mega, right? Mega is 1024 by 1024. It's not 1000 by 1000. What's that?
Because it's 2 for
Could you not just do 128 or 512? Or 128 mega?
Yeah, 128 mega byte. Oh, 128 megabytes. Yeah, mega is this times this, right?
Oh, okay, so it's just, I see.
Yeah, these are bytes. These are bytes. This is also bytes. Make sense?
But mega is 1024 times 1024,
Yes.
not 10 to the 6.
Not what?
Not 10 to the 6, like we did for like frequency.
Oh, no. Nope. Oh, megahertz. That's right. That's why I got confused, right?
Yeah.
When we talk about megahertz, it's not a binary stuff. It's just a million. We just refer it to million. But when we talk about the bytes, megabytes, kilobytes, it's 1024.
It was close, but it's not exactly.
Exactly. Yeah. That's why we do it, because there's no way that I get an integer in the tens base numbers, right? So 2 to the 10th power is going to be 1024, right? It's a binary system. It's not a decimal system. Okay. So you can calculate how many bytes you have in there, right? How many bytes? So you need how many entries, how many addresses. Okay? Then you calculate, this is 2 to the what? Seems like you need 27 bits at least. But usually we don't use 27, we don't use 28, we don't use 29. We don't even use 30. And we hate 31, which is like 32. Why? Because it's 2 something, right? It's 2's force power, yeah, right? I mean, integers of 2's multiples. Oh, yeah. Make sense? 2 to the 16s, 2 to the like 32s, 2 to the 64s, like this. Anyway, so we only need I don't know, you calculate it. How many? I think it's like 27 bits or something. But we choose to use 32, okay? 32 bits. So here's a question. Did we figure out all the questions on the exercise 2? We don't have to finish everything on the exercise 3 anyway. Let's see. I don't talk about 7A. So what about 6? Oh, 6 we just did it, okay? 7. How do you print out the higher? Okay, yeah, we just talked about this, right? How to print out? Yeah. How do we do that? You got a 32-bit data address. It's a 16 by 16, right? Oh, print out lower and higher 16 bits individually. So this is a 32-bit data in the PIC system. If you directly print it out, you are trying to print out the 16-bit data. Let's say print hex number, right? For example, it's called SD card address. So how do we want to do it in order to get the higher one printed out? So for example, you are printing out 16 bits each time. I don't think the serial is gonna do a 32-bit printing really well. I think we had a assignment somewhere, but I didn't stress that. But eventually you should know that when you are doing the printing function, the size here, maximum use 16 bits, don't use 32 bits, it's getting errors each time. So byte by byte is perfect, but 16 bits is also fine.
So if I just put up in the thing, you said that, is there a page per, was that calculation that you showed determine the number of pages?
Yeah,
Oh, okay, so that's the number of pages, and that determines, the number,
Yeah.
okay, so 128 pages,
yeah.
okay.
So this one, every time just print out 16 bits, don't do more, okay? So if you want to print out this one, what do you want to do? Shift, right? Shift. Shift by what? Just do it. You already give it the answer.
Shift right.
What about the lower one?
The X is just gonna print out one of the numbers, though, isn't it?
Yeah, you can directly just print out the lower ones. If you just directly print out this guy, it should. If you don't, so here you have to shift it for the higher, right? The higher 16 bits. But for here, if you want to do in the lower one, the thing is, you don't want this one to throw errors. So I think the strategy here for the code that we used is trying to use this 32-bit address, doing a bitwise AND with what? With a 16-bit here and 16-bit here. So it's extracting the lower 16 bits exactly, but canceling, resetting the higher ones. So printing out the lower ones by doing a bitwise AND.
So just print out.
Could you do a bitwise AND with like the first four, like F.
This guy?
0, 0, 0?
No, you shift it. You shift it. Shift this one. After shift it, this becomes 0 automatically.
That would just be a right shift by 4, correct? Or by 16.
I don't know. Close.
But if it was in, it's just fine too.
Okay, the last one. Still have 6 minutes. What does the following loop store in the buffer? What's the block size? 512. SD card buffer bracket I will store how many points in there after the for loop? Everyone can see that, right? I don't have to show you, it's gonna have solutions on it. You have it, right? Okay. So how many bytes are stored in it after the for loop? It's just the for loop stuff.
512.
512. Okay, 512. So what are these numbers though?
It starts at 255 and then it's going to go all the way down to negative 255.
But these are unsigned integers.
Unsigned integers.
Mm-hmm.
Then 255 all the way to 255. Does it like loop back around with overflow?
Yeah, it's overflow. It moves down to 0 and then underflows, right? It's called underflows. Underflows.
Yeah.
Underflows and 0, 0, all zeros minus 1 is what? All ones, right?
Right. Which if it's in
And
it would be
then
255 again.
yeah, you got to physically all ones in the memory in the register, and then that all one starts decrementing again. So it's basically from 255 goes down to 0, and then do what?
Then go back to 0.
255.
Yeah, and then
0.
yes. Is that clear? Any question on this?
Is I a UNT 18 then? Are we just assuming that?
I is what?
8-bit integer?
Yeah. Wait. No.
Because it wouldn't underflow if it was like a 16-bit integer.
No, it's I is index is holding like it should be 16 bits because it's holding 512, right? So A will be 256 at the maximum.
ST core buffer is the one that's the 8-bit integer, which is why we get underflow.
Okay.
I'll give you a few minutes to finish up that and turn it in to get your benefit credits. Again, please fold it like this,
I'm thinking about it.
and so I can open it up on the right. Not here, not here, not here. And read it clearly. See, this one is right. Oh, this is yours, Sophia. This is also right. This is also right. This is also right. This is also right. 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 See? See? Please. I want to make my grading easier. It's 100 assignments. This, here, okay? What about this? Correct. See? See? Can we just follow? Can we just follow? Just do this. Okay? Alright. Please turn it in. I'll see you on Thursday.